Okay. Okay. So thanks for the invitation again. Yeah, it's a pleasure to come here, to be here. So let me start. I think I just wanted to say, continue on last time's bit of the reciprocity law. So what happens is, see, if I have what do you call a representation of the Galois group, right? So then you can look at what is called the decomposition group at some prime p or whatever it is, and which is so it's a Galois group of a number field. Say I'm looking at the ring of integers, say OK, say over Z or whatever it is. So then I'm looking at all those automorphisms of the Galois group, which fixes, say, the prime. Yeah. So I'm looking at all those automorphisms sigma, which sends OK to OK. That is, of course, that sends OK to OK. And then there is a prime P, sigma of PV is equal to PV. And what we have is then this is the decomposition group at the prime V. And then this decomposition group maps to, because sigma preserves this, it goes to the Galois group of OK mod PV, the finite field, over Z mod PZ. And a very elementary counting using Chinese remainder theorem or whatever tells you this map is surjective. And so, and if it is an isomorphism, then that place PV is called unramified. It's unramified. It's unramified if it is an isomorphism. Right? And so then what you get is that you get a generator for this. This is a cyclic group, and a generator for this is called a Frobenius conjugacy class. One fixes, you have a choice of two generators. At least you normalize it so that sigma v of x is congruent to x to the power p, because I'm taking this mod p. So that's a Frobenius conjugacy class. So what happens is, when I take a general Galois, if I look at Galois group of, say, K over Q, and take some representation, say, let's take GLNC or some field. Then for most primes, this is unramified. So V is unramified for most primes. All but finitely many. So then you can attach, for every such V, you can attach sigma V. And you can, so what you can do is to, if I look at some combination NVV and V is unramified, I can send it to summation product sigma V to the power N. Okay, so these are what are called divisor classes, but which are co-primed to this set of bad places, finite set of bad places. So you have a map from what would be called the ideal of S. These are ideals co-prime to S. So by prime factorization, any such ideal I is product of some primes PV to the power NV. And this, we are sending it to summation NV times sigma V, or rather, not summation, product sigma V to the power NV, which belongs to the Galois group. Okay. So the statement of the reciprocity law, in some sense, is that this map from, so what happens is, there is a natural map from from the local field. So the local field, the completion KV star, it maps to Z, which is the valuation map. This is the valuation map, and this we can send it to, you know, you can send it to the ideal groups by sending 1 to PV, and so n goes to PV to the power NV n. So what happens is this map I can think of it as product KV star V naught in S, and this goes to map to IS, and then you have a map to the Galois group of K over Q, right? So okay, I don't have to put KV star whatever it is, but somehow this ideal group, in some sense, what one is saying is that the part of the reciprocity map is that formalism is that the continuity with respect to the congruence topology when K over Q is abelian. So when K over Q is abelian, then there is a continuity with respect to the congruence topology. With respect to congruence topology, that will allow us to extend this map to all product. This is what is called a restricted product, KV star. It's a restricted product to the Galois group of K over Q. Right. So this is what is called the group of ideals, JK. Yeah. And then, so what is reciprocity? So reciprocity in this formalism of Chevalier is to say that the kernel is precisely equal to K star. So what you get is that there is a map from JK, the ideal mod K star, which is called as the group of ideal classes, and this is the reciprocity map K to GK. Of course, here now I can go into what is called the GK abelian, which is the abelianized Galois group. Okay, so that is what is called the reciprocity map, which comes, and this is the formalism in the sense of ideals and ideal classes, and it kind of takes away some of the confusion or whatever you get from looking at the Artin formalism of reciprocity law. So this a good reference to see this is Tate's article in Cassell's Frolic. In the beginning, he tells you what this continuity and other things are. Right? Okay, so that is what's happening out here. Now I just want to make a remark about so this is so far what we are looking at is the one-dimensional case of what is called class field theory or abelian thing. Now, for some reason, people expected that there will be non-abelian generalizations of the classical reciprocity law. Right now, I can't immediately think of it. No, this is GK abelian, which is Galois group of K bar over K abelianized. Here I should have taken K over Q abelian. So I'm taking K over Q abelian. Implicitly, I'm assuming this is an abelian extension in this. Otherwise, I would have to deal with Frobenius conjugacy classes, in which case, anyway, I can't take the product like this. Because it's commutative, I can do this product. So I should have said that, yeah, I'm here, I'm working with Galois group K over Q abelian. This is in the abelian case. Thanks. Yeah, right. Yeah. Yeah, so for some reason, so we'll come to some of it a bit, this thing, but I don't know precisely what was it that led people to suspect or expect that there will be non-abelian reciprocity laws. But anyway, so what's happening is that one expected non-abelian reciprocity law. So this is for the, you are only getting a description of the abelianized Galois group. Okay, so the non-abelian reciprocity law is, okay, let us say it this way. Right? Okay, why we want a non-abelian reciprocity law? So what the abelian reciprocity law also, if you look at it, what it says is, as we saw, um, in the sense of or Zi or Qi, whatever it is. So we can take a prime P, and if a rational prime P times Zi, which we saw, it either breaks up as a product of two prime ideals, P is odd, P is not equal to 2, P times P conjugate, P bar, or it remains a prime ideal. So this is called the split case, and this is if and only if P is congruent to 1 mod 4. And this is P is congruent to 3 mod 4. So the reciprocity law amounts to understanding how a rational prime splits in the number field, abelian field, which you are looking at, quadratic fields or whatever it is. So now what you are looking for, if I'm trying to look for a general number field, for instance, a soluble or whatever it is, so you would like to say what is the splitting behavior of a prime in the ring of integers of the number field. So what you want to understand is the splitting behavior of primes, that is in a number field. So to put it more, this thing, take a polynomial whose Galois group is, suppose I'm assuming K over Q, and say the Galois group of K over Q is given by the Galois group of some polynomial whose splitting field is K. And you would like to know what, for most primes P, what is a set of how many irreducible factors it has, which means it will for most primes P, the polynomial will split as it will be a separable polynomial when you go mod P. And what you would like to know is, this is P is an integral polynomial. So you would like to know how it splits, what are the number of factors it has, irreducible factors. So that is a splitting behavior, and you want to understand that. Okay, so the problem is somewhat very this thing. So understanding the reciprocity law in general, one first approximation is what its arithmetical content we don't know yet, because we don't understand anything apart from abelian reciprocity law, right, at this stage. But you would like to understand what this thing is. So the question is how do you relate it to some whether you get some good arithmetic information or not, right? So you would naturally expect that what you would like to do. So let me put this figure out here. So you have a map from CK, the ideal class group, to GK abelianist, right? But now you're not looking at abelian extensions, you're looking at general extensions. So which is, GK abelianist is a quotient of GK, right, by the commutator subgroup. So what you have is a map which is GK, which is here, right? So what Weil asked is, on the other hand, the reciprocity law from the point of view of whatever Chevalier or Artin is that you have this group of ideal classes which has been manufactured purely out of information coming from the field K. This is giving you extensions L over K of abelian extensions. Okay. In fact, the congruent subgroup topology also tells you that the fields which correspond to this, right, are congruent subgroups here, essentially. Okay. So if I take a congruent subgroup which is a finite index, then CK mod that group is the Galois group of whatever that field which is corresponding. So it's a very beautiful explanation of the abelian reciprocity in terms of this idyllic formation. So the question is, since CK is manufactured out of K in a very nice manner as this thing, do you have some group which maps like this, which is there, right? So that is in order to expand the reciprocity law, if I want, I would like to find a replacement for CK in the full Galois group case. So it should have the thing that I should be able to give you a map to the Galois group whenever I'm having this kind of conjugacy classes and other things. And the one-dimensional theory should be that of CK. That means I want WK abelianized is isomorphic to CK, and that should be a map from WK to CK. So that is the first conditions you want to put. And what you try to do is to part of the importance of the reciprocity law is just not only the reciprocity map CK to GK abelian, but to also know how the reciprocity map behaves with respect to field extensions and this thing. Suppose if I have a map, if I have L, K is contained inside L, then you have map from CK to GK ab, from CL to GL ab, and there are maps from GK ab or GL ab, whichever way, and then how are the reciprocity maps related? Or you can have a norm map from L to K or whatever it is, you can have a corresponding norm maps. How does it reflect on the side of the Galois abelian group and other things? So what happens is, so you put the corresponding conditions on the definition of this group which you want. Okay, right? And so in a sense, one can see that it kind of rigidifies the group. It's unique up to some kind of uniqueness and such things. And that is called the Weil group of a number field or a local field or a function field, which is there. Okay, so that is a Weil group. Unfortunately, what happens is this Weil group is good enough for, there are what are called 4 cases. One is number field, then a local field of characteristic 0, a local field of positive characteristic, and a global field of positive characteristic. Except for the number field, for all 3 others, this is a good group. We'll come to why it is a good group. But for a number field, it is just falling awfully short. Okay, it doesn't really have any decent representations apart from irreducible representations coming from GK and some what are called dihedral representations induced from index 2 subgroups. So it doesn't have a rich enough representation theory. So the Weil group of a number field is not what you want. It's not what is the Galois group or the motivic. Okay, but keep this in mind, because if we have time, we'll come to that later. Yeah. So, but now, yeah, I just want to say one remark out here. So the proof of the quadratic reciprocity law kind of whatever it, I don't want to, I can't, but there was a key idea coming from what is called the Chebatrov density theorem, the proof of the Chebatrov density theorem by Chebatrov. So what happens is, which is saying that the Chebatrov density theorem says that this conjugacy classes which you are getting from the for every prime p is kind of equidistributed with respect to the normalized measure on the collection of conjugacy classes, right? Because if I'm working with non-abelian things, I only get a Frobenius conjugacy class, not a Frobenius element. That's what is well defined. And so on the Galois group of K over Q modulo conjugacy classes, you can give the measure where Galois group of K over Q as whatever is the measure 1. So on conjugacy classes is the relative size of the conjugacy class. Okay. And what the Chebatrov density theorem says is that the conjugacy classes are equidistributed with respect to this normalized measure on the projected measure on the space of conjugacy classes. Yeah. So it's an amazing theorem because you're saying something for so the Chebatrov density theorem is a generalization of Dirichlet's theorem on primes in arithmetic progression, right? So you're able to say something for any any finite abelian group. It can be non-commutative, not be this thing. But you're basically reducing it to the case of the abelian. Okay, so there's a fabulous reduction which is going on there, that of reducing it to the abelian case, the proof. And so this is, it's not that this thing, but what you have is, you need to know the analytic properties. If you have seen Dirichlet's theorem of primes in arithmetic progression, you have to know the analytic properties of Dirichlet characters, right? Ordinary thing. And what it's not that Artin had said something about, if I have a general representation of the group, to attach an ordinal function, and it should have some, possibly some analytic properties, but that cannot be proved. But instead, you can still prove the Chebotarev density theorem, which is by reducing it to the analytic properties of Dirichlet characters, essentially. So that is a thing. So that, okay, so that is the one from coming from Dirichlet's from Chebotarev density. But what Chebotarev density theorem as a consequence says that if you know the splitting behavior of the primes and whatnot, then this number field is uniquely determined. Okay, so if you I suppose maybe up to Galois conjugacy, but yeah, anyway, yeah, up to Galois conjugacy, yeah, well, up to conjugacy. But since I'm working with Galois groups, K over Q is Galois, so then the splitting behavior determines for you what Galois group you are looking at. Okay, what field which you are looking at. So that's a pretty thing that so the understanding the splitting behavior, it determines for us the number field, and you don't focus on the polynomial because the polynomial is not the correct thing, whereas you have to focus on the number field. And so this would be considered as a generalization of the reciprocity law. So this is still not known, of course. Only in A5 cases, you know, because of. No, it determines the number field. Okay. No, I'm working with K over Q Galois, right? So it determines the number field, of course. Because if I have two different number fields, you can find one element which will split in one another and doesn't split in the thing. So you know that the splitting, just the primes which split completely determine the number field. Okay, Galois, I'm assuming the extension is Galois. Just the primes which split completely.
Doesn't depend on result arithmetically equivalent number fields?
No. The arithmetically equivalent number fields is the Gassman thing, right? So which is to say that, but that is if I'm looking at non-Galois, right? So see, the question is, suppose if I have two number fields which are the same zeta function, right? Then are they necessarily Galois conjugate? So you are now assuming that these fields are non-Galois over Q, all right? And what Gassman's example says is that yes, you can very easily produce such example, which is Artin or whatever Gassman's idea, by this thing which is there. But what Dipendra was asking, that thing which is see, the point was, it was known that you can have what might be called Gassman equivalent number fields, and but the class groups need not be isomorphic. So these were examples coming from the great Dutch school of number theorists, who are, I think, very good in both number theory and computation. It's a or maybe it might be known before, but I know these examples were by one of those people which is there. So you can produce number fields which are the same Hasse-Weil zeta function, right? And but the class groups are different. The point is, if you look at the class number formula for the zeta function at the residue at s equal to 1, then it has in it the regulator, the unit regulator, the discriminant, the class group, and some roots of unity and some factors of pi and 2 pi and all this number of real places, number of complex places, all of them are embedded the information is encoded in it. So what you expect from the analytic data is, you don't expect this to be, this information is the same. But if you look at from the point of view of geometry, when you're doing various things, you only expect isogeny in some sense. Isogeny means finite information will always be lost. So you can't expect class groups to be the same in some sense, because they are finite. The finite things can be butchered around in an isogeny. So what Dipendra was asking is not the paper with me, but the thing was something somewhat similar to this, that whether some integral things are fixed on the nose, and that can never be, because even in the geometric case, when you're looking at Jacobians and other things, you only get up to isogeny. Like Faulting's theorem, which tells you that the zeta function or whatever, the Galois representation, it only determines the elliptic curve or the abelian variety up to isogeny. It will never get it on the nose, which is there. So you can't expect very strong isomorphisms even if you have Galois conjugate, or not Gassman conjugate things. So you can't expect everything. So you have to allow a finite error all the time. Thoda to masala chahiye. So that is a part about that. Of course, one has to get a counter example, and that was done from using some group theory. Okay, so this is a kind of thing about the wave group, and I've said what the things. Now let's come to a slightly different story, which is modular forms. Now somehow in a lot of all these things, many times just to understand the one-dimensional character itself is the first step, and if you understand that, then some things are more easier. But anyway, so this is a different. So the first initial examples of modular forms were what are called the theta functions. So these are the theta functions of Jacobi and this thing, and it's a, that by Lagrange or whatever it is, if every natural number can be written as a sum of 4 squares, then the question is, in how many different ways can you write a number as a sum of 4 squares, or a sum of 10 squares, or 200 squares, or whatever it is. And the way to do it is, suppose if I take 200 squares, then I look at x1 squared plus x100 square, right? So that's you want to know whether in how many ways can you write this number as a sum of this thing, sum of 100 squares. So what so what you look at is basically and this is of course Euler had the idea of trying to look at it as a power series product of summation x to the power n squared, say 100 times, and the coefficients give you the number of ways of representing a number as a sum of 100 squares. But this is not the correct function to do. The correct function is to look at something like e to the power I pi, maybe, I don't know whether you have to put I pi, of q, this quadratic form. Am I saying? And then so you look at where tau is in the upper half plane. Tau as imaginary part of tau is greater than 0. Or maybe I should write it No, it's a function. Q of something. Q of Qx equal to no, I'm summing over x in the lattice. X and z and all. Z under. Yeah. Maybe, yeah, right. So this gives you summation e to the power I pi n tau. N is the number of the number of expressions where n is equal to x1 squared plus x100 squared. Yeah. Okay, so the point is that this theta function satisfies some modularity property, which arises because of the Poisson summation formula relating Fourier analysis on Rn to Fourier analysis on Rn mod the lattice. And so they give you a space of holomorphic functions on the upper half plane modulo your suitable lattice, maybe SL to Z or whatever it is in this case, which have the property that the corresponding space or whatever is it's finite dimensional. So then, because of finite dimensionality and other properties, you can figure out in some sense this number of representations by trying to explicitly construct what are the theta functions or modular forms which you have. Okay, but that is a classical story. I don't want to get into it. I've not really, prepared my notes on that or whatever it is which is there. So there is one other case which, so this is the classical way. So the other way is that it comes from the elliptic curves, right? So the classical, see the elliptic curves are parameterized. So this is what would be called, so geometrically this is a curve of the form C modulo gamma. Gamma is a lattice in C, right? And now this is analytically, if you want to see it, this is the moduli space of doubly periodic meromorphic functions with doubly periodic with respect to this lattice. So what the Weierstrass theory tells you is that such a curve, you have a map to projective 2 space or C, and with a very particular thing. So this curve is defined by some, I'm not writing now in projective coordinates, but we can write it if I want. It's 4x cubed z minus g2, which depends on the lattice x times xz squared minus g3 times z cube 4x. Yeah, maybe there might be some plus minus, but and the point is that the g2 function, which depends on the lattice, so the g2 gamma is summation 1 upon lambda power 4, lambda belongs to the lattice and lambda not equal to 0. And similarly g3 yeah, so these are functions which, when you work out the Weierstrass theory, you get these functions. So these are called the Eisenstein series of weight 4, but these are the holomorphic functions, so you weight 6, and they have the property that this g2 of lambda gamma is lambda to the power minus 4 times g2 of gamma. So this is the homogeneity property with respect to scaling which you have, right? So what in this language, what you're looking for is you're looking for functions f which are defined on the space of lattices, which satisfy f is such that f of lambda gamma is say lambda power, one knows you can't get lambda power minus k times f of gamma. And for some reasons of holomorphicity or whatever it is, this k is a positive natural number. Okay, and that is called the weight of the. Okay, so the point is that okay, these forms are there, but what Ramanujan did is to consider what is called the discriminant of this, which is maybe g2 cubed minus 23 gt squared. Okay. And as I said, the space of lattices, okay, so that's a form which one looks at. So now what you get is that so there is an action of GL2 R on the space of lattices. Right, just a standard conjugacy action, because and you look at, for instance, if I want to and say GL2Z is the isotropy group of the standard lattice Z2. Right, so GL2R mod GL2Z gives you the space of all lattices, and then you're also going more low, some kind of scaling by lambda. So when you look at the space of lattices modulo this scaling, what you essentially get is the upper half plane modulo the action of SL2Z. So what I would like to say is that the space of lattices up to scaling, this space is isomorphic to upper half plane H modulo the action of SL2Z. So what happens is that you can use this to translate what's the definition of a modular form in this language of functions which have some behavior with respect to SL2Z. Okay, so right, but now we want to look at the group theoretic properties of this modular forms. So one of the first things which so this was a program by Gelfand, is to transfer whatever was done classically in analysis, whether it's a notion of Whittaker functions, whatever, anything, Fourier, all those things, everything Legendre polynomials, whatever, any substances which you see in classical analysis in terms of group theoretic formalism. And one of the things was to recast a notion of a modular form in terms of group theory and representation theory. So what you do is a modular form, so I can consider f as a function on GL2R by GL2Z, right? Basically, GL2R acts on the space of lattices with GL2Z as the isotropy group. So I just look at the value of this modular form on the lattice which it corresponds. So I immediately get a function on GL2R mod GL2Z. What Gelfand you realize is that when it is of weight k, and if it is holomorphic or whatever it is in a suitable sense, then this gives you functions on the group which or so they're kind of the GL2 span, the yeah, so it gives you a function on the space. So the representation, the so GL2 acts on this group on the left, so I can look at the translates of that function and consider the vector space which is spanned by this. The translates of F under the GL2R action for suitable forms, it generates a, if I close, an irreducible representation for the holomorphic forms. It's what's called a discrete series. This is a discrete series of weight k. Okay, I'm fudging details a bit because in order to do this, you have to take both the upper half plane. Yeah, maybe on the lattices, it's fine. If I work on the space of lattices. So this gives you a discrete series of weight k on GL2R, right? Okay, so this is a thing which, of course, Gelfand did that, but this was before that. The notion of modular form, when you translate it to the group, these are holomorphic modular forms which you get. So you could also construct a real analytic theory, which was done by mass. And when you do the mass functions for the mass, forms, which were actually invariant functions on upper half plane mod gamma, but which are eigenfunctions with respect to the Laplacian, hyperbolic Laplacian. The representation which you get is what is called a principal series representation. And one can correspond the eigenvalues with respect to the Laplacian to that of whatever is the parameterization which you have for GL2. No, GL2, I am not yet come to that days.
So F infinity is F is the same.
This is F infinity.
Yeah, F infinity.
Right?
And this is on the SO2, it will act by e to the power h.
Yeah, this will act on the weight will be given by the mass forms are already invariant under gamma in the classical setting. So under K it will act trivially. Mass forms will give you principal series. Underline field. Yeah, sorry.
So I mean, this discussing it was the cusp.
Oh, sorry. Yeah, I need to assume some cusp form. I am not yet getting to that thing. I need to. I'll assume cusp forms. But maybe you don't need to assume cusp form. You probably need a growth condition, maybe to recast it in terms of representation theory. But cusp forms will tell you that it lives in the space L2 not of GL2 or right? That is. So otherwise, the Eisenstein series. So okay, so yeah. So now, so as I said, there are three types of modular forms which I have to do. One is the theta functions, which I'm not really going to touch upon because they don't fit into the eigenform picture so well. Okay, so it's probably still one of the problems. Maybe Manish might say or whatever it is of how to fit theta functions into the Langlands formalism, but of the functor reality. Okay, so the the form which we are trying to look at is this delta. So, but I want to define what are the Hecke operators in this setting. Okay, right. So what's happening is I'm looking at, so as I said, GL2R acts on lattices, and you have GL2Q also acts on the subgroup. Okay. Now, what you find is, suppose if you take a lattice gamma and you're letting gamma is an element out here, small gamma, and you look at gamma times acting on gamma. Now, because it's GL2Q and it's very close to being GL2Z, the denominator is, these are integer matrices with some finite denominator. Gamma gamma intersection gamma is a finite index inside gamma. Okay. So what you do is you have a function which is defined on all lattices, right? So you look at the function on the group which is defined out here on GL2R on the space of lattices. So you look at F, right? The action of T gamma is, wait, yeah, let me, okay, so, right. So I want to define the Hecke operator for weight n, right? So what you do is you look at the matrices in M2, 2 cross 2 matrices with integer z, which have determinant equal to n. Okay, so this is what would be called, so you can multiply this collection of matrices both on the left and right by GL2Z, because determinant 1 they are right, or determinant plus minus 1, whatever, SL2Z. So this is a double coset under the space. So what happens is this is a subset of SL2Z. It's so this, when I write it, it's a disjoint union of SL2Z, some finitely many elements gamma SL2Z. Okay, and what the Tn operator acting on function f is, you basically average summation of I think you have to look at what is called f stroke gamma is, I think it will be the same. So you look at f of gamma gamma intersection gamma over running over all this. So TNF on gamma is this function. I hope I am right. I am not. No, I'm taking the representative. These are finitely many representatives. Yeah, but since I'm thinking of it already as a function of the lattices, I don't have to do f stroke gamma. I think I'm skipping. See, only when I go to that picture and then I will have to come back, then I have to do the f stroke gamma. But I'm already working on the lattices, so then I don't have to do that. Okay, I think so. Okay, but I have not checked it. But the point is that there is an action of GL2Q or whatever it is on the space of lattices. And in some sense, you have this subgroup SL2Z, which is an isotropy group, right? And so what is happening is that your modular forms, when I look at this averaging property and because of this homogeneity property, these operators are acting in a sense continuously on the space of modular forms with respect to the topology given by what you would be called congruent subgroups in SL. See, when I look at gamma gamma intersection, I think you declare this subgroup as an open subgroup, discrete subgroup, which is of the thing which is the isotropy group, because the isotropy with respect to the SL to Z is one dimensional. So this is, when I look at it at its action, this is a discrete subgroup. You call this as open. It's an so yeah. So you look at the topology and GL2 or M2 cross 2Z modulo this modulo SL to Z cosets, and this action is continuous, and then you complete it with respect to this action. So that's how the Hecke operators are coming in. So I think when you look at it from the point of view of lattice functions, I think these operators automatically look natural, which is that it's basically the fact that GL2Q normalizes GL2Z in a suitable sense that so if I look at gamma inverse GL2Z gamma, where gamma belongs to GL2Q, so this subgroup is intersection GL2Z. This group is a finite index in both out here and out here. So if you have a function which is invariant under GL2Z, you can look at f stroke gamma. It will be invariant under this group. Make it consider it as a function of the subgroup, and then average over the coset representatives of the other. So that is the way the classical Hecke operators are defined, and because of this factorization that every n can be written as a product of prime numbers, I could have as well taken n equal to p, and that gives you the operator with respect to p. So for when I look at matrices of determinant p, then I'll be having p001 and one more. I think that's the only representative, no, and 100p. Yeah, these are the two cosets which you'll decompose. Yeah, I can think of it as 1 upon p times p001. So not a, times some data. Yeah. Okay. So the Hecke operators are coming in, and then what you find is that the Hecke eigenform, the Ramanujan delta function is an eigenform for the Hecke operators. Okay. But what Langlands saw is that if you topologize this space with respect to calling this subgroup SL2Z or whatever GL2Z as an open subgroup, and the continuity of the Hecke operators with respect to the congruent subgroup topology, then the natural thing is to complete. If you want, you think when you take the completion, it was known that when I take the completion of GL2Z or GL2Q with respect to the congruent subgroup topology, then you get finite adels, GL2 of finite adels. So what happens is so GL2 finite adels AF is the completion of GL2Q with respect to the congruent subgroup topology. So I don't know a place where this is explained well.
So what you are saying is that if you start with a subgroup of finite index of SL to Z, then only the corresponding automorphic representation phi F and exists on a identity group. Right? So you are taking comparison with respect to congruent subgroups. If you start with non-congruent subgroups, it won't give you any automorphic representation. I'm saying
No,
contrary.
the problem is with the non-congruent subgroups.
Suppose you start with the finite index subgroups. Okay, all this is finite non-congruent. So for you is like
Wait. See, there is a. See, you want a theory of Hecke operators to be there, right?
Yeah, but
the theory of Hecke operators, what you need is to say that there is a large group of. See, the point is that this property is satisfied for gamma and GL to Z.
Sure.
That gamma inverse times GL to Z, gamma intersection GL to Z is of finite index in both these groups.
Yeah, so I assume let's take subgroup which is a finite index for non-congruent.
In both the subgroups. So here GL to Z is a congruent subgroup of 0 level. If I take a non-congruent subgroup and try to do it,
no,
right? No, I can take a non-congruent subgroup of GL to Z. Any subgroup of finite index which is not really a congruent subgroup.
Yeah.
Then the collection of such gamma is finite.
Okay.
Yeah. So this is a theorem that arithmetic subgroups, arithmeticity or whatever it is, this later a theorem of Margulis that
that is quite popular in here.
Yeah, no, but the point is that the Hecke operators exist only when, in some sense, when the commensurator group is large, and when your lattice is arithmetic, then the commensurator group is what is called the group of Rajan. So these are the ones which manages to push around the lattice up to finite error, and then you can again do the averaging and get the Hecke operators. So you get the Hecke operators only when you are working with arithmetic lattice.
So this is a paper by Margulis.
No, in the sense of in general, but see, when you go into anyway in higher rank groups, there are very few non-arithmetic subgroups. All lattices become arithmetic, so it's not a. And then the condition is that for arithmetic, one can see that this is the full commensurator. The question is that if it is non-arithmetic, then it is this group is basically it is gamma, or it's a normalizer, the normalizer of gamma or whatever it is inside the commensurator group. Gamma inside the commensurator group is of finite index if it is non-arithmetic. That is so you don't have Hecke operators in the non-arithmetic. Yeah, so this is and so what happens is, because these modular forms are continuous with respect to this congruent subgroup topology, you can define this as a function on the Adenic forms, and f infinity gets defined out here. So via this you can define what the Adelic version of what a classical modular form is. Okay, right? But more than that, following whatever Gelfand or whatever, the Hecke operators and other things are now looked up as representations of the Adelic groups. So there's one more aspect out here, is that when I look at the full level, see, suppose if I look at GL2, say QP, or GL2 OP, the ring of integers ZP. Right. So the convolution, the algebra of convolution of doubly invariant functions, this becomes abelian. Okay. And in general, when I'm looking at this full level, this group breaks up as a what will be tensor product over all these primes P, and this is an abelian algebra which you look at. And turns out that the Hecke operators or whatever of one should be able to see it from purely from this lattice theoretic or whatever it is, that the Hecke operators are self-adjoint. And so you can do a spectral theory and ask for eigenfunctions with respect to the Hecke operators. And the first primary example is the Ramanujan delta, which is there. Okay, sorry, it's a yeah. See the Hecke operators classically, for how to look at them, part of it is explained very well in Shimura's 1970 book. But going to this completion, I don't know where it is explained well. It's
I have not seen it.
no, yeah, it's I don't know where it is explained well, but yeah, but the Shimura's 1970 book, one should have a look. It's a really great book which explains many things, especially CM theory and all. Probably it's the best place to read about CM elliptic curves. And okay, so yeah, now what Langlands functoriality or whatever is saying is that what Langlands, okay, so there's a third set of modular forms which you want to look at, or what are called this Eisenstein series, but not the holomorphic one. These are the real analytic ones. Okay, so they played an important role in discovering the conjectures. So the Eisenstein series is the classical, the real analytic Eisenstein series is Z is the upper half plane. It's whatever some you look at imaginary part of gamma Z to the power, I suppose, minus S. No, to the power S. And where the imaginary part is fixed by this thing. So you look at what is called gamma by gamma infinity. Okay. So the group of whatever triangular matrices. So this is basically summation 1 upon mz plus n to the power 2s imaginary part of y z. Yeah, y to the power s. Yeah, and yeah, where mn or coprime. Okay, I can never remember my formulas correctly. Mod, no, here it is probably y to the power 2s. This anyway is mod of mod.
So y to the power s.
Y to the power s.
No?
Y to the power s.
That's yeah, y equals to that's
Y
fine.
to the,
Yeah, this is fine.
this is
Y.
yeah. But so the point is that this function has some, so
Yeah, so you have to put s equals to where the s times s square for the s.
yeah, for the convergence to hold.
Yeah.
So the Eisenstein series is in some sense, I would say, it's a deformation, or let me use this word boldly, not that I know understand, a quantization of the Riemann zeta function. Since no physicists are around. Okay, in the sense the Riemann zeta function is a GL1 theory, whereas the Eisenstein series is something which is happening on GL2. So, and it's also it's spreading it around, and you are doing something which is lifting it to something on GL2R or whatever GL2 of the alleles. Okay. So the point is, for instance, this is fairly important in many ways. So you can also look at zeta 2s times EZS, and the advantage is here it's the summation is over mn co-prime, and here it is over m maybe 2s y to the power s, but overall integers mn, so that mn non-zero. There is some factor out here, half or whatever, something like that. And usually what one does is to add pi to the power minus s gamma s and call this maybe the completed function E star z. Okay, so the point is that E star zs behaves almost like the Riemann zeta in the sense it has a I think E star z 1 minus s as a functional equation of this kind, and also it has a Fourier expansion. E star zs is I think zeta star by this the completed product times y to the power maybe 1 minus s or plus minus 1. Maybe this and this might be changed. I'll take it with a pinch of salt. The exact expression might be there, plus this is what would be called the constant term or the Fourier expansion, plus some Fourier expansion in terms of Bessel functions. Fourier Bessel expansion, summation some n greater than equal to 1 or something. Okay, so the fact is that you can go between the Eisenstein series, the real analytic properties of the real analytic Eisenstein series, and that of the zeta function. If you know that the Riemann zeta function, this zeta star s is the standard pi to the power minus s by 2 gamma s by 2 zeta s, for which the function equation is satisfied. So this is the third type of Eisenstein series, the third type of modular forms. So you have modular forms, one which is the cusp forms, which the Ramanujan and others that generalizing the Ramanujan. You have the real analytic Eisenstein series, which are in some sense and other holomorphic Eisenstein series which are generalized, which are there. And you have a relationship between the Eisenstein series, which should be considered as probably some kind of modular form on the bigger group, to that of GL1 theory, which is the Riemann zeta function. And you can go back and forth between the analytic properties of this function of the Riemann zeta to that of the Eisenstein series, or if you know the Eisenstein series analytic continuation, which is because of this unfolding trick that you can do it over all Mn not equal to 0, 0. It's easier to prove the analytic continuation of this. Okay, this is the Rankine kind of unfolding trick which helps in the thing. So from that you can also derive the analytic continuation of the Riemann zeta function, or if you know the analytic continuation of this, you can get the function equation for that. Okay, so it's also you can use, for instance, the Eisenstein series to also show, for instance, it's a proof due to Jacquet and Shalika that you can show that the zeta function is non-vanishing, for instance, on the real part s equal to 1 using this Eisenstein series and this Fourier Jacobi expansion, Fourier Bessel expansion. So the in some sense, it I would like to say that it's the Eisenstein series which seems it has a far more better structure, more complicated to study, but it's a better structure in some. What it should be viewed at is a function for each S. It has values in the principal series on GL2R mod GL2Z. Okay, so it's kind of living as a it's a section. It's Fourier expanded. It's like when you're doing the Fourier transform, the eigencharacters for R are e to the power ISX unit. But when you're doing it, you're looking at it as a continuous integral of those representations of those characters. So the Eisenstein series, in some sense, are giving you sections for the collection of principal series on the modular group, which is there. Okay, so in some sense, these are valued on the collection of the principal series which are there. So it has far more structure than this Riemann-Zeta function, which is.
So this Eisenstein series was there before Langlands. So
the real analytic Eisenstein series was mass. Mass. But
so what in this Eisenstein series before what Langlands? What is the?
So the point is for GL2, Selberg did the analytic continuation for the Eisenstein series, and what Langlands did is to do it in full generality.
Okay, for general
reduction. And then he found that if you look at the constant terms, you are getting the L functions of constant of cusp forms and other things. And so he could show that the ratios of this L function values have analytic continuation, meromorphic, which is of course Chandrashil and Rajan. But if you look at the Fourier expansion is slightly more, then you can get the analytic continuation of the L functions of LS prime. That is a Shahidi's method, which is there, right? With Langlands-Shahidi method. Yeah. So, but it also seems to, but maybe even for analytic properties of automorphic L functions, maybe it might be better to go to the corresponding Eisenstein series and look at it. But I would think it should be better because it has slightly more structure in the sense of the values in representation theory. But even in the arithmetic world, Bhaskar might the thing or whatever it is, that it is this Eisenstein series which allows you the relationship. See, the crucial to this Ribet of Wiles method is that you can construct the Eisenstein series in an integral manner, and at some primes p, they look like a cusp form. And that congruences between semi-cusp forms. So the congruences between cusp forms and the Fourier and Eisenstein series gives you the various deducibility results which you need for your class groups and other things for proving converse to Herbrand, which is that you have to show some.
So for me, it starts with, I just follow this Kubota. Is there something better than that? Kubota,
by the way, there's
for GL2. I understand for
there's a nice book by Ribet and Stein. Have you seen those?
Yeah, of course, that is there.
I didn't know this.
Okay, that is there. But for real analytic Eisenstein series for GL2, for me, it's like always Kubota. There's something better than that. Just this real analytic.
I think
these people, they just.
You should ask either Bhaskar or you guys should decide, or Chandrashil should decide. Amongst three of you, what should be there? Sorry, these people?
No, there is automorphic world, there is a result. Okay,
no, but
this real analytic Eisenstein series, I started looking at it from Kubota's book. Is there any something? It's just.
No, but when you are trying to do all this, the periodic theory for things which are going beyond GL2, whatever Skinner and using.
Sure, that
so then you will be using, right? You have to use other Eisenstein series in order to get that.
That is there, but I'm saying this real analytic Eisenstein series for GL2.
Yeah. what is the arithmetical significance of this?
No, no, no. I understand the arithmetic. Is
Ah,
there any
no.
reference better than this? Okay, never mind.
We'll see. I can't immediately.
Yeah.
Yes. Any? Okay, I don't know. Wait. Yes. Okay, so yeah, so
Also, try to.
yeah, okay. I just wanted to say a bit about the Langlands functoriality, but see the one of the first points. Okay, just 5 minutes. I'll just think is that okay? One connects up with representation theory, but uh, the Langlands functoriality says that in some sense modular forms on different groups are to be related, and there has to be a dual group which should parameterize the thing. Where does a dual group enter? Is that so? There are, if I look at GL2R, the representations are of basically two types, three types, of course, complementary, but there are this principal series which is induced from characters on the this thing. If I look at A1, A2, and then star, whatever. So you look at this character which goes to A1 to the power S1 times A2 to the power S2. Okay. And then induce it, think of it as a character on the Borel, and then you can do the induction and you get this unramified principal series, not non-unitary, but whatever it is. And then you have the discrete series. Right. So the idea is that if I have to look at the parameters for this is I look at S1, S2 because it doesn't depend on the order doesn't matter. So you just need a conjugacy class. So this defines a conjugacy class in GL2C. Right. Now for the discrete series, the conjugacy class which you have is that okay, so what you expect is okay for when I'm working with, say, for instance, GL2C, this is enough. This because all representatives of principal series. But for discrete series, the Weyl group of R, right, it maps to Z mod 2Z, and this is Weyl group of C, which is C star. One can see that. Okay, so you can look at a representation, a character of C star, and induce it to a representation of WR. So you get a dihedral representations which are irreducible, and those ones correspond to the discrete series. So when Langlands was trying to look for these parameterizations, he found that using Harishchandra theory, say the representations of a group G, say defined over R, they correspond to representations or whatever it is of WR, say suppose let me say JLNR or JLNC, WR roughly to, let me say, to JLNC. Okay, which is compatible with this Z mod 2. I should not say GLNC or yeah, anyway. Roughly, you have to look at the L group on this side. So there's it's maybe so should say L of GLN over R, but that is like GLNC with a Z mod 2 action. Yeah, which is that. So what happens is that so this is amazing that first of all, you have this, conjectures which we expect, and the first evidence for Langlands is that for representations of a real group, real reductive group, or parameterized basically by representations of this simple group into GLNC. So that gave him the confidence that this conjecture should hold. And so the local Langlands for a general p-adic field is to replace WR by the local Weyl group. But on the other hand, the global Weyl group doesn't have sufficiently many representations. So you will have to postulate for it a different group, which we don't know it exists. Sorry, yeah. No, there is no ideal classes. This is just real numbers and complex. This is only local, just local.
But instead for the global field is started. Then
global field, the Weyl group is not such.
The dietary representation that you are getting here correspond to
which one? No, here it's only on the Weyl group side. I'm not working on that.
Langlands have infinity.
then you don't get index to.
Yeah, of course. The other thing is, yeah. Anyway, I needed to. Yeah, I thought I could say a bit about the trace formula, but I don't think. Okay, so let me, since I think probably this is the first time, so first time I said it is probably at Pune. I always like this. What the trace formula I was just telling. So if I have a group G, then one knows there is a duality between representations of G and conjugacy classes. Okay. What Langlands is looking for is not all representations of the Adele group, but you are looking for representations of G occurring in functions of G mod gamma, because these are the modular forms which are living there, right? And this, what trace formula says, is in duality with conjugacy classes of gamma in G, of elements of gamma in G. Okay, so when you write it function theoretically, that is the trace formula which you have, right? So, so this is really the trace formula. And so what, if we want to do this functoriality or this shifting, for instance, symmetric square or other things, so what you would like to get, you want to have a correspondence at the level of representations, you try to first establish a correspondence at the level of conjugacy classes. But this conjugacy classes or whatever, when you are doing the symmetric square lifting or any lifting, is only done at the level of algebraically closed fields. Now, but whereas the trace formula is living out here on G mod gamma, which is not algebraically closed. So there is a discrepancy between conjugacy classes over the ground field and conjugacy classes over the algebraically closed field. And so that leads to something which we'll leave Manish to talk about, endoscopy and right. That was, sorry, yeah, right. Yeah. Yeah, right. For this full level, it is.
Is this the reason that's why the characters of the cell is because it's coming from
yeah, that is called the Hecke algebra. That is Hecke at P. But this is a commutative thing. You can also look at more deeper congruent subgroups or other things, but then that algebra will be non-commutative.
No, I mean, all those also can make sense of this global algebra.
Yeah, but globally, if I do it at full level structure and whatnot, then that becomes abelian and it breaks up as a tensor product of this. That is because of the same thing, that I can, every integer n breaks is a product of prime numbers and other things. So, the things the double cosets, you can write it up with things of determinant, various factors, and then the product and convolution. See, when you compose two double cosets, then the take the product. So if you have a determinant n and determinant m, it becomes determinant n. So that way you can decompose the. Yeah. So it breaks up as a tensor product of the local factors. And anyway, it's because you are working in the commutative phase, you can write it as a tensor product. The point is that in some sense, these groups are very special, maximal in some sense. See, if I want to look at in a classical case, if I look at the Cartan decomposition for a group, if G equal to K times A times K. So if you look at the Hecke algebra with respect to K, that is doubly invariant function, then it basically depends on A, which is commutative. So you have something like what is called a Gelfand trick or whatever it is in this case, that if you have fixed points of an involution or satisfying some property, then the convolution algebra, double coset algebra will be commutative. And these are hyperspecial maximal compacts or something. So you get this commutativity, which is yeah. So yes, when it is commutative, it's understood that when you go into the correspondence between representation theory and Hecke algebras of lower level, I think the best place to understand is this Bernstein-Zelewinski notes. The first thing, it's a very well explained there. How you see these things? Yeah.
Depth, higher depth.
Higher depth, the correspondence between Hecke algebra modules and representation.
So now we can describe it completely. Now.
No, you have much more explicit description. Yeah, but the very general theory is yeah, right.
So, yeah.
But what are you saying? Sorry. Yeah.
Bernstein has a endomorphism of Bernstein projector that description.
Yeah.
So it doesn't work out as generic representation for a general Bernstein plot. So this is the trivial principal series block
which is
capturing.
This is
and here you also have the advantage that you are taking GL.
Yeah, GL of course is it's for the other groups that the entire theory starts. Yeah, any further questions you can address it to Manish or Devaga, Chandrashil, or Bhaskar, or all these people who are there. I don't know why I'm talking such stuff when all these guys know that stuff. So it's I think highly stupid of me to.
This is targeted towards graduate students.
Yeah, but I think even the graduate students probably know this stuff. But you know, it's.
Sir, is there any good reference where this Langlands subgroup topology that topology completion?
Yeah, that's what I see. The point is, some of these things I learned it long back as a student. I can't immediately recall. Yeah, we'll do that.
I also want to just always quote that for identity comments.
Yeah, but yeah, maybe one should just work it out. It's not too difficult from here to do that. But that is, I think the observation is basically probably due to Langlands, and who also showed that the representation can be factored into local components of the adelic group. So one can do that. Not even Satake, I think. But yeah. No, this is all. I think it just comes in the beginning. I think it just comes out, and people don't even notice that it's probably due to him. Because see, the Gelfand's interpretation in terms of representation theory probably came in the 50s, and then the Gelfand, Piasecki, Shapiro came only. That book came in the mid 60s, right? Or so. But before that, it was known, this connection with representation theory, and Harishchandra knew it. Okay, and Harishchandra even said that apparently that anybody who does analytic continuation of Eisenstein series and interprets a constant term will hit the jackpot. He said that. Okay, will hit the jackpot. He apparently said it very precisely. So, and Langlands did it. So Harishchandra immediately. So who see that paper of book of Langlands on Eisenstein series? I think maybe Harishchandra would have known it. Arthur knows it. Walsperger probably knows it. And and I don't think anybody else probably does. As Arthur says, only when you come to the last but one page, do you understand what the proof is about of the thing. So it's an extremely difficult book, and people have tried doing the analytic continuation using simpler language. But what Langland says is when you go into deeper parabolic subgroups, not rank one, that's where the entire difficulty blows. And for rank one, he still feels you can get other methods, but more than rank one, I don't think even Bernstein or anybody have been able to make an impact about what this analytic continuation is. Yeah, but right. So yeah, that's a. But yeah, so that is a this thing. But yeah, so this congruence completion is it must be there somewhere. Somebody must have explained it. But GL1, as I said,
That possibly gives you a new perception of these ideals.
no, that's what, no, that's what was Chazale's idea in doing ideals. No, what was that? He recast the reciprocity law in terms of ideals, because from the ideals, he called it ideals because these are generalized ideals, right? But see, when I was trying to write notes today in the morning, I was getting stuck quite royally, not in the sense of from the conceptual viewpoint. See, the group of the free group generated by ideals of S is z to the power number of whatever, some infinite number of copies for each prime not in S. Why should I involve this thing, the ground field KV star? But see, if I have to go to the ideal class group, then basically I'm thinking of it as a quotient of KV star to Z. So I'm thinking of it as ideal classes on Z. But maybe if you are taking right, so it's not at all clear why ideal classes should come on the reciprocity side. It's only Z to the power S in some sense it's coming out. But the continuity is with respect to the congruence topology coming from product KV star to this. Which is because you still don't know what, see, and what you're saying is that if I know what is happening at the good primes, somehow that forces also the behavior at the bad prime, because the reciprocity law will tells you what this is. So you can also get the local class field theory from the global, knowing what is happening at the good prime. But suppose if I know local class field theory, right, then which means there is a map from KV star to the Galois group of the abelian maps, which is there. But I still can't see why it has to be formulated in terms of ideal classes. As it is, I can think only in terms of ideal groups. But the ideal class group coprime to S is a direct sum of or Z infinitely many copies. Ideals, right? Because by prime factorization, that is just product Z or direct sum Z, infinitely many. So it is not KV star. So why is that coming in ideal classes? So I have it's when you look at it, it's but yeah. So it's really nice, because otherwise the Artin formulation is to say that you look at IS, you have this map, and then it satisfies some kind of reciprocity which is not totally clear. You define what is called the Ray class group, right? No, no, I thought it's wrapped up.
So let's try and speak the question.
Sorry, it's a wrapped up. People have. Maybe I should switch off the microphone.